G'day! Some 2,300 years ago, the Greek geometer Euclid proved the following result about circles. It appears in his work The Elements, Book 3, Proposition 16, and it goes as follows. Take a circle, draw in a diameter, then choose one of the endpoints of the diameter. I choose this one. Well, let's do it pink. All right, I'll choose that one. He says, construct a line through the endpoint like this. Make it 90 degrees to that diameter. 90 degrees to that diameter. Then he managed to prove that this line will never touch that circle again. The only point of contact between that line you just constructed and the circle is that endpoint you went through. That is, there's only one point of contact. This is a tangent line to the circle. He showed how to construct tangent lines to circles. And all throughout the ages, scholars worked very hard to try to find tangent lines to other special curves, parabolas and the like. And they had some success, but only very limited success. Finding tangent lines to curves is really, really hard. And the big breakthrough came with the invention of calculus in the 1660s. In fact, this is the idea that Newton proposed. Do the following. I can work out tangent lines to all sorts of curves thinking this way. Here's his approach. Suppose you've got some curve. Suppose you know the formula for that curve, the graph of some function there. And suppose you want to find the tangent line to, say, the curve at that point right there. So since you know the curve, you know the coordinates of that point. You said, okay, I don't know how to quite find the tangent line, but I could find the equation of a secant line. Choose another point on the curve, whose coordinates I presumably I know, in which case if I know the coordinates of 2 points, I know the equation of that line. There's a secant line. He said, okay, that's not a very good approximation to the tangent line, so then choose another point close to the point you're interested in. Do the secant line, say, between those two. He said, okay, to get a better approximation, do an even closer point to the point you're interested in. Get a secant line between those points, and so on and so on and so on. Keep doing this over and over again. So in some sense, he was saying these secant lines want to go to some limit position. In fact, he was using the idea of limits here. He was saying in some sense, so here's my loose language, the tangent line will be the limit position of the secant lines. Secant, if I can spell things, secant lines, as you choose points closer and closer and closer to the point you're interested in. Okay, very strange idea, but he was using this all based on the notion of limits. And using his theory of limits, he could actually figure out ways to get tangent lines to all sorts of curves. Amazing, a big breakthrough, But it relied on the notion of limits. But what's completely surprising is that before this, two gentlemen in particular, Fermat and Descartes, were actually working out tangent lines to all sorts of curves, polynomial curves, without any notion of limit, without any use of calculus, using pure algebra. In fact, Descartes published his results in 1637, but then actually figured a way to do a simpler version of his results a year later, which he wrote about in letters to his colleagues. So what I just shared with you today is the purely algebraic way to actually find tangent lines to polynomial curves using the ideas of Fermat and Descartes, and maybe some modern ideas too. All right, so let's get cracking. This is going to be fun. Okay, since we'll be playing with polynomial algebra, let me spend a moment playing with polynomial algebra. Here's the key result we need. If you divide a polynomial by a quadratic term, then I claim the remainder you'll get will be a linear term. Oh, that's very abstract. What do I really mean by that? Well, the best thing is to do an example. So here's a polynomial f. Call the name f, and it's given by f of x will be 2x to the fourth minus 5x cubed plus 5x squared. And let's divide it by a quadratic term. X minus 1 all squared is definitely quadratic. All right, I claim if I divide this by that, out will pop a linear term, mx plus b, something like that. All right, let's do it. Now, of course, those who know me know I'm going to do this the exploding dots way, so feel free to look up exploding dots to see what I'm doing. But here is a base x machine. 1's x squared, x cubed, x to the fourth. Yep, that's as high as I need. X squared, whoops, x cubed, and x to the fourth. Let's be a little bit neater, James. And I want to represent my polynomial f with 2x to the fourth. So I need 2 of these. So I'll do actual dots. Say got 2 actual ones of those. I want negative 5x cubes. I want anti-versions of having those. I want one antidot. I want 5 antidots, 5 anti-versions of those. And I want 5 actual x squared, so 5 dots of those. All right, there's a visual representation of my polynomial. And I want to divide by x minus 1 squared. So let me just expand that out quickly to see what that looks like. It's x squared minus 2x plus 1. So in a base x machine, that would be 1x squared, 1 actual x squared, 2 anti-x's, and 1 actual one. All right. So division. I'm asking you, how many groups of these do I see in that? Well, for me, visually, it is seeing how many groups of this pattern do I see in that pattern. So that's a visual way to do polynomial division. And I look at this right away and I say, okay, I am seeing dot, double anti-dot, dot right here. Dot, double anti-dot, dot. That's one copy of exactly what I'm looking for right there. I'm seeing one copy at the x squared level. In fact, I see another one underneath. Dot, anti-dot, anti-dot, dot. There it is. So there's really 2 at that level. So algebraically, I'm seeing 2 at the x squared level of this thing, x squared minus 2x plus 1. All right, let's keep going. That's cleared. Oh, there's a single anti-dot there. And there's a double dot there. So it looks like I'm going for the anti-version of that. So there's nothing here right now. So I've got anti-dot, double dot. I want an anti-dot there. Keep the box empty. There's a consequence of me doing that. So that box is still technically empty because now I can see an anti-version of what I want. That's the complete opposite of that. I've got negative ones at this level, negative one of those. So I've got negative 1 at the x level. Oops, orange, sorry. Whoops. I've got negative x, one of these things at the negative one of these things at the x level. There we go. And finally to finish this off, what have I got? Anti-dot. I would love to have, no, that's an actual dot, sorry, my handwriting, that's an actual dot. I would love to have 2 anti-dots there, so let's put them in, make it happen, deal with the consequences. Dot, double anti-dot, I need a dot there, make it happen. I just did, and that gives me 1 at this level, 1 at the level, so I see one of these things at the ones level, one of these 2x plus 1, and what am I left over with? Remainder is 3 at the x level and anti-1 at the 1 level. So there's a remainder of 3 at the x level and 1 at the anti level. Double check. If you want to expand this out, that is my polynomial f. That's my expression for my polynomial f. So I can actually see now, oh, the remainder is a linear term. Something that involves just x's and constants. No x squares, no x cubes, and so forth. Brilliant, brilliant, brilliant. And this one example can illustrate that actually when you always divide something by quadratic, all the remainders will be pushed into the final 2 boxes, in which case all the remainders will be x's and 1's. Bingo, combinations of those. All right, but here's the delightful surprise. I claim this is the equation of the tangent line to this curve at x equals 1. Whoa. So this is a slick way of presenting Descartes' result. I claim, let me just give myself some space. Where am I going to do this? Okay, maybe here. If I've got a polynomial f, and I divide f, let's do it in some fancy colors, orange. If I say f of x and I divide it by a linear term, a quadratic term, x minus a squared, you will get some quotient, plus some remainder, mx plus b, still weighted by x minus a squared. The claim is, if f is a polynomial and you do this algebra, then this remainder here is then y equals mx plus b is the equation of the tangent line to y equals f of x at x equals a. Whoa. So there is a slick version of Descartes' result. So what I need to do is explain that. But let me do it via Descartes' thinking. Let me show how Descartes got through his work. That actually will then lead us to explain this beautiful algebraic approach to get tangent lines to polynomials very quickly. It will all make good sense to us. This is kind of cool. Okay, to illustrate Descartes' approach, let's just try one example, this one. Let's compute the tangent line to the curve y equals x squared at x equals 3. So here's the y equals x squared graph. At x equals 3, we'll have a height of 9. We want the tangent line to the curve going to the point 3, 9. All right, we don't know what the tangent line is going to be, but we do know it's going to be of this basic form. Y is some slope x minus 3 plus 9. They have that correct. Put in x equals 3. Yes, you get y equals 9. Great. So there's the general equation of a line through that particular point. All right, but we don't know the value of m. There's something, what special value of m do we need to choose? So here's Descartes' approach. He said, okay, we've got this equation we're playing with. We've also got this equation we're playing with, okay? And actually, if you look what we want this system of equations to have only one solution. To be a tangent line, it should only have one solution. Okay, so let's actually play with this. There should be only one value of x and one corresponding value of y that makes this pair of simultaneous equations valid. In which case, if I look at this part equaling this part, x squared equals mx minus 3 plus 9, to reduce the equation of just one variable x, there should be only one value of x for which that's true. Okay, so let's play with this quadratic equation. It should have only one solution. So we need to choose a value of m so that it only has one x value, one solution. Okay, so what am I going to do here? Well, let me bring let me bring everything to the left. X squared minus 9 minus mx minus 3 equals 0. We want that to have only one solution. X squared minus 9, that's x minus 3, x plus 3 minus mx minus 3. We want that equation to have only one solution. I have a feeling I'm running out of room, so let me just do this. We'll go back up here. I want this equation. Let's bring out the common factor of x minus 3 times x plus 3 minus m equals 0 to have only one solution. We want to choose the value of m that makes sure that this has only one solution. Well, one solution is x equals 3. Clearly, putting x equals 3 is going to give me 0. So this better be really x minus 3 again in disguise. It really should be x minus 3 again in disguise, in which case m better be 6. M better be 6. Oh, there's only one possible value of m for which this has only one solution. M is 6. The equation of this tangent line must be that. Pure algebra and logical thinking. Whoa. Okay, that was kind of cool. Let me do it again. Let me do it again with more generally. Let's do it at not just x equals 3, let's do it at any old point x equals a. So let me change this to an a. So what's the general equation of a tangent line to the parabola y equals x squared, x equals a, which means I'm now changing this and this and this. So what happened? Here's a, must be height a squared. We want to look at these equations, y equals x squared, and the y equals the tangent line, x minus a plus a squared. I believe that's correct. Put in x equals a, and yes, you'll get height of a squared. Bingo. This pair of simultaneous equations should only have one solution. If it's a tangent line, one solution. In which case, in particular, if I just focus on the x stuff, x squared equals mx minus a plus a squared. This quadratic equation should have only one solution. It should have like a double root, if you want to call it that way. Let's bring everything over to one side. X squared minus a squared minus mx minus a. That quadratic has only one solution. Common factor of x minus a here. I can do it again. Pull out x minus a. That'll leave an x plus a behind minus an m equals 0. So this equation should have only one solution. A is a solution. This better be x minus a in disguise. In which case we must have m being negative 2a. Am I right? Yes. No, 2a. Should be 2a. X plus a, take away 2a, would be x minus a. We must have m equal to a. That is, the slope of the tangent line at x equals a is 2a. And if you know calculus, you know that's right, but there it is. So the equation of the tangent line in general is 2a, the slope x minus a plus a squared. Pure algebra. Wow. Okay, so here's Descartes' insight. We've got the graph of a nice polynomial function, and we're trying to find the equation of the tangent line to that curve at some specific location, x equals a. Now we do know the equation of the tangent line is going to be of the form y equals some slope times x minus a plus f of a. I think I'm right, putting x equals a to that, vanishes, y equals f of a. Yes. So there's the general form of the equation of the tangent line, except we just don't know which particular value of m for slope to choose. And his insight was the following. We want only one solution to these two equations, at least one solution right near x equals a. So we set f of x equal to that, there should be only one solution, and that will give us what value of m to play with. At least it did in my quadratic examples from a moment ago. In fact, we realized that our quadratic examples were giving us double roots. We're getting x minus a squared was the final equation in the end, going for a double root. He said, that's it. It's the double roots, the multiple roots. So he says, okay, here's the approach I suggest you take. Let's look at this function minus that function like we were doing before. We were writing f of x minus m, x minus a minus f of a in my previous examples. But let's see if you can try to find a value m so that this really is something with a double root. It's x minus a squared times something. If you can do that, Descartes claimed, if you find that special value of m that does the trick, then yes, that really will be the equation of the tangent line. That special value of m you find that works there is the slope of the tangent line. That's his insight. Whoa. And for us, it really was working because every time we did it moments ago, our something was the number 1. So we had x minus a squared times 1. Yes, yes, yes. But Descartes claimed that this is the general setup that's going on. That if you've got this situation happening, then that forces this part here, this linear equation right there, to be the tangent line. There it is. That will have to be the tangent line. So let me see if I can prove that. If I can prove that for you. Why would that be the case? So let's see. Let's keep that picture on the board. So what have we got here? Let me rewrite this again. This is telling me that f of x equals our line, x minus a plus f of a. Did I get that correct? Except to keep going right neatly. X minus a plus x minus a squared times something. All right, so let's think about this. So I've really got this equation that my function is my line plus a bit more, it looks like. Except I'll be very careful about signs here. So let's think about what this something could be. Now, in the world of polynomials, this is a polynomial. This is a polynomial. This is a polynomial. So this something, whatever it is also a polynomial. It's definitely a polynomial. So everything here is polynomials. So in the world of polynomials, and my something is a polynomial. And I'm very interested in what it's doing at x equals a. So it's going to have its own little graph. Let me do this, my own little graph. So here's my graph of my something. At x equals a, it'll be a nice little graph like that. Oh, maybe. I've drawn it with a positive value at x equals a. And by how I understand polynomials, if it's positive right there, it's going to be positive or near there. Which means, what I've got here is f of x equals this line plus, that's always positive, plus in my picture this is a positive, plus something always positive. In fact, that's what I've drawn here. My function is always my line plus some extra stuff. In which case, yes, it really is a tangent line. Add extra stuff to my line, and I'll get up to my function, and they're both equal at that point. That means they only touch right at that point. So right near x equals a, this really is the tangent line. Yes, yes, yes. If my something is positive at x equals a. Now actually, if my something is negative at x equals a instead, if my something had a graph more like this, went down to negative there, then this is always positive times at least around x equals a, it's always negative. This will always be a negative number. So my picture will be kind of upside down. My graph is my line, take away some stuff. So it must be my graph must be under my line. Now they equal at x equals a, but now my line, take away some stuff, gets me down to my function, in which case I have a tangent line as follows. Great. The only troublesome spot is when my something is also 0 at x equals a. If my something has a graph like this, where it's actually changing sign, then this argument goes out the window. I mean, you might be able to salvage it if it doesn't actually change sign. Maybe it's 0 there, but it sort of stays positive, or 0 there, it stays negative. That would be fine. It's when it actually changes sign at x equals a, things are troublesome. So what are we going to do about that? Well, let's do something. Let's do an example where that something does change sign and see what we think of it. But I need to clean my board, so back in a moment. All right, let's find the tangent line to the curve y equals x cubed at x equals 0. So here's the y equals x cubed graph. It's a nice S-shaped graph, something like this, like that. And we want to find the tangent line at x equals 0. and that's also where y equals 0. So at the origin. Tangent line to this graph at the origin. So let me follow Descartes' method. So we have one equation, y equals x cubed. We have the other equation, y equals m, x minus 0, plus the value at 0, 0. I guess not a very much of an equation. It's going to be some line through the origin, so I could have just said that from the get-go, some slope times x. All right, I want just one unique solution to those two equations, at least near x equals 0. That is, I want x cubed equals mx to have only one solution. Bring everything to one side, x cubed minus xm equals 0 to have one solution. Common factor of x squared minus m should equal 0. This should have only one solution. Only one solution. Well, it's definitely got the solution x equals 0, in which case this better be giving me only x equals 0 as well. The only option for m is m has to be 0. M has to be 0, in which case my line is the line y equals 0 times x. It's always 0. The line y equals 0 is the horizontal x-axis. The tangent line must be that. Which is awfully strange, because when you look at, when you're in geometry class, you've got now suddenly a tangent line that actually cuts through the curve. Is that allowed? Well, this work seems to suggest it is allowed, and you know what Descartes said? We'll go with it, we'll go with it. This mathematics is saying, yep, tangent lines can actually cut through curves in this special way. And what's really interesting, if you do calculus, you'll see that calculus says exactly the same thing. This really is the tangent line to the curve y equals x cubed. From Newton's approach, he came up with the same ideas. Tangent lines can indeed cut through curves in this special way. So Descartes went with it, and we'll go with it as well. All right, but let's keep playing, because I'm having fun. Okay, so here's Descartes' general result. To find the equation of the tangent line to some polynomial curve y equals f of x, do the following. Find the value of m so that f of x minus m times x minus a minus f of a, all this stuff is really x minus a squared times something. Get a double root in there. Get a double root, at least a double root. That's grand. Because then he claims you find that special value of m, yes, then m is the slope of this tangent line, and that's the actual equation of the tangent line. It all comes together. All right, so to practice that, let's try to find the slope of the tangent line to y equals x to the n at x equals a. All right, so let's go follow Descartes' work. What we need to do is look at this quantity, f of x, x to the n, minus m times x minus a, minus f of a, that'll be a to the n. And we're going to try to write that as x minus a squared. So hopefully get to this x minus a squared times stuff. That's what we're hoping to get to. All right, so I'm going to play with this. So I'm going to play with this. Yeah, all right, let's play with it. Equals x to the n minus a to the n. That's a very sort of a standard polynomial thing to play with in class, because it has a factor of x minus a. And I bet if you do polynomial division, you will see this is x minus a times this stuff. X to the n minus 1 plus a x to the n minus 2 plus a to the n minus 2 times x plus a to the n minus 1. But if you expand it out, I bet you can see it lots of stuff collapses, and in the end you're left with an x to the n and a negative a to the n. All right, double check that. But that's this part, and I've still got a minus m x minus a. There's a common factor of x minus a. Let me pull it out. So this is really x minus a times all this, x to the n minus 1 plus a x to the n minus 2 plus all the way down to a to the n minus 1. And then there's still a minus an m. Still a minus an m. All right, so that's what we've got so far. I'm going to erase the middle stuff to make this less visually cluttered. So our goal is to try this, to get this to be x minus a squared times stuff. And right now I've just got a single x minus a. All right, so this is where we're just crossing our fingers. We have to try to find a value of m that works. So if there is a value of m that works, that means we need an extra x minus a. This must have a factor of x minus a in it. This must be x minus a times something for this to work. Okay, without doing any of that, I won't do that division. I won't divide that. That's too hard for my brain. But if this is equals x minus a times something, and if I actually put in x equals a, I'd get 0 times something. This should be 0 at x equals a. If it does indeed have an extra factor of x minus a in it, then it should be 0 at x equals a. So I deduce we need this to be 0 at x equals a, if we've got any hope of finding a value of m that works. So let me just do that. Let me do what that says. I need all this to be 0 if I actually put in x equals a. So that tells me I need, okay, put x equals a to the n minus 1, plus put x equals a minus 1, plus put x equals a, plus a to n minus 1, put x equals a, there was no x's, equals m. I need all that to be 0 if there's any hope of a value of m working. In which case, that tells me what m should be if I've got any hope of this working. And by the general theory of Descartes stuff, this should be working. So what is that? This is, how many of these things are there? Looks like there's, you go from a to the 0 to a to the n minus 1. There's actually n of these. There are n of these. Oh, this is brilliant. So the only possible value of m that could work is m being n copies of a n to the minus 1. We must have m equals n copies of a to the n minus 1, which is indeed the result you get from everyday calculus of taking the derivative of this and putting in x equals a. There it is, without calculus, without any limits, just the pure reasoning of the algebra. This is pretty amazing. Okay, let me go back to the very first algebraic approach I presented in this video of Descartes' work. Remember, we said back then, if we divide a polynomial by a quadratic term, in particular by x minus a squared, then the remainder you get is sure to be a linear term. So that means if I take any polynomial, f of x, if I divide out a factor of x minus a squared, so I'll get divided out x minus a squared times something, I'm going to be left with a linear term for the remainder, mx plus b. Alright, so there's the polynomial algebra that I first presented in this video. And let's just play with that equation right now and see how that links to Descartes' work. If I put x equals a, that seems curious because I'm not quite sure what that b is, that's new to me. Put x equals a, whoops, I'll get that f of a equals 0 plus ma plus b. So that tells me a formula for b is f of a minus m of a. Alright, so let me put that in there, because now I know what the actual full remainder looks like. It'll be something times x plus f of a minus m of a. I can do that. Erasing it, got it in my head though, because I can see I get plus f of a minus m of a. I'm really seeing this as plus m of x minus a plus f of a. Alright, so basic polynomial algebra, if you divide by a quadratic term, you'll get a remainder that looks like that for some specific value m. But look at this. This is exactly the same setup of here. That is, this is saying if you divide out by x minus a squared, you could write f of x minus m of x minus a plus f of a equals x minus a squared times something. Bingo! Beautiful, beautiful. And, that's a minus, sorry, minus, and my handwriting is terrible because I'm so excited, forgive me. Handwriting is terrible, f of a. That is precisely the setup of Descartes' work, in which case, yes, that remainder is exactly the tangent line to the curve. Whoa. So you can just divide polynomials. You want the equation of a tangent line to a polynomial at x equals a, divide it by x minus a squared, see what the remainder is, done, because that's Descartes' work tells you are done. This is stunning. This is beautiful. During the 1600s, other mathematicians also played with Fermat's and Descartes' ideas. In particular, Dutch mathematician Jan Hoodt, if that's how you pronounce his name, and Isaac Barrow, an English mathematician, were definitely playing with these things. And in fact, Isaac Barrow discovered something amazing. Now, he was actually considering graphs like this. He said, suppose I've got a nice function that's positive and increasing. And for some reason, he was playing with areas under this graph. Areas under the graph. This was in the air at the time. So he said, okay, I'm going to define the area function as follows. I'm going to let a of a be the area under the graph from x equals 0 to x equals a. So here's a point A. He said, okay, I want the area under that graph from x equals 0 up to x equals a. A of a is that area right there. So So definitely have an area function now. In fact, you choose different values of a, I'm going to see actually I get bigger and bigger areas. So I get another increasing function. But he really played with this and he discovered the following remarkable result. He said, okay, let me look at different positions. Let's look at his fixed position A, but let's choose another position, say x, that's to the left of A. And he played with this picture and said, okay, all right, look at this. I can look at a of a minus a of x, that is, all this area, take away that area, would leave me with this pink area right here, pink area right there. Great. In fact, you can see that this pink area is definitely smaller than the area of that rectangle there. In fact, that rectangle is height f of a. He says, oh, that area is definitely less than the width, which is a minus x times the height, f of a. All right, so just rearrange that equation. Let's see if I can get this right. Let's bring this on this side. So I'll make it negative. So I'll switch that around. X minus a times f of a plus a of a is less than the area under x. So he came up with that general formula for points to the left of a. But here's the amazing thing. The same formula, he realized, holds for the points to the right of a as well. So let me clean my picture a little bit. So let's not focus on this part. Goodbye pink. So I've got all this green stuff now. He says, okay, instead, choose a point x to the right of a and do the same idea. Look at this area here. All right, now, let me get rid of that definition so I've got some space. Sorry, gentlemen, off you go. Now to the right. Now if I look at this pink area, that's the area all the way up to x, a of x, minus the area up to a. That's what this pink stuff is. And that is definitely greater than the rectangle this time. It's actually greater in area of width, x minus a times height, f of a. And if I rearrange this formula, I can see that x minus a times f of a plus, bring the a of a over here, a of a is less than a of x. Exactly the same formula. It's exactly the same formula. But look at this. Look at this formula. This is a number. This is a number. That's x minus a. This is actually the equation of a line. He's managed to find a line that's always under the area function. A line that's always under the area function. A line of slope f of a under the area function. So Sir Isaac Barrow discovered the following result. I'm going to say it in clunky words and I'll put it in modern notation. If f is a positive and increasing function, then the tangent line to the area function at x equals a has slope f of a. He managed to figure out the slope of the tangent lines to area functions. But here's the thing. Today we call that the first fundamental theorem of calculus. No calculus, just algebra here. He essentially showed this. We let a of x in modern notation be the area under the curve from 0 to x. And he just showed that the slope of the tangent line of an area function is the curve you're dealing with. Bingo! There's the first fundamental theorem of calculus without calculus. Amazing, amazing stuff.